Hi, welcome to State Space Modeling with Tim. This is the fourth example of the series, and it is slightly similar to the first example we did in the series. However, this one is a bit more complicated. The first example had only one mass, and this one has two masses which are interacting with one another. Interesting to see how that will pan out. We're gonna try to use the steps we have outlined throughout the first example, going to the second example and to the third example. But for this one, we're going to try to play with the steps so that the question can flow and the solution can be found a bit quicker, because this is a very big problem. So without wasting any time, let's get working. So the first step, because this is a mechanical system, is to draw the free body diagram. So we're just going to draw a free body diagram right next to the problem itself. Okay, so the only actual body we're going to draw is going to be the mass. It's going to be the first mass, and then we're going to draw the second mass just slightly lower there. Okay, that's done. So we're going to first focus with the first mass and see which forces are acting on the mass. Okay, so let's start up with the upward forces. The first force acting on the upward mass is this K1 spring, and then the second force is the C1 damper. So we're just going to draw them pointing upward. Okay, so this one, the net motion is y1, that's the displacement of the mass, and then I just want to draw this one y2 as well while I'm at it. Okay, so the net motion is y1. So the spring one, we can just specify the force. It's just going to be k1 multiplied by y1, and this is just Hooke's law. And the damper is going to be c1 y1 dot, the first derivative of y1. Okay, now we can write the forces that are acting downward on it. The forces acting downward on this mass is going to be its weight, first and foremost, and that's going to be given as m1 multiplied by the acceleration of y1. So that's going to be the second derivative of y1. Okay, and now we can look at this spring here that's interacting. So it is obviously because of the weight pulling down on this mass. So we're going to write it as downward force, and this is going to be K2. Okay, and we can say K2 Y1. Okay, so now we can move on to M2. M2 only has the spring, and we can look at this M2, we can look at the spring as if it's pulling upward on the mass, because it's the only thing that's holding the mass from falling down, assuming gravity exists, which shouldn't be a crazy assumption. And so we're going to start to make things easy. We're going to start with the weight of the mass, which is going to be m2 multiplied by the gravitational acceleration, and that's going to be y2 dot dot second derivative. Okay, so that what we talked about something that's pulling at this weight, at the weight, forcing it from reaching the ground, and that's the spring action. So that's going to be K2 Y2. Again, Hooke's law. Okay, so the forces meet here in such a way that they are not necessarily equal, but we know K2 is equals to K2, obviously. So what we can do, I'm going to write this in green, is we're going to say that K2, okay, sorry, let me write it like this. K2 Y1 minus K2 Y2. But we have been given a restriction here. I'm just going to write it and quickly run to red. It says this system, for this particular system, oh, sorry about that. I should be connecting this to the charger right about now. Give me a minute. Okay, so for this system, K2 is equals to Y2. No, K2 is equals to K2. Sorry about that. But Y2, for this particular system, Y2 is greater than Y1. So this should be reversed, in fact, because the net motion is going downwards around the spring. Y2, and this one is Y1, because of this restriction here. So if Y1 is less than Y2, then the net motion is downward. So it has to be K2 minus Y2. And then everything else should be straightforward here. So before, in the previous examples, we said that the first step is just to come up with the differential equations. For this one, we're going to start off by actually pointing out what are the system outputs, system inputs, and the state variables. So let's do that now. So I'm just going to write it here. Sorry. System outputs. Okay, looking at the system now, the output will be the displacement, which is something which should be easily observable and measurable. So Y1 and Y2 are our outputs, Y1 and Y2, and our system inputs. Looking at this, it is clear that our system input is this external force P of T and nothing else acting on the system. Okay, and then the state variables. Okay, so we have, what are our derivatives here? So remember, I made this strong hint from the first example that one way to see your state variables is to look for those variables that have derivatives. Look for the variables that are being differentiated, and it's no exception here. Here, the only thing we have being differentiated is Y1 and Y2, and we can see that it's being differentiated all the way to the second order. So if Y1 is differentiated to the second order and Y2 is differentiated to the second order, it tells us that we're going to have 4 state variables. And I'm just going to point them out now. And I'm going to say Y1. And yeah, so we're basically going to select them in terms of x, in terms of our x variables that we've been using throughout. So I'm going to say properly, let x1 equals to y1, and I'm going to say x2 equals to y1 dot. Okay, I'm going to give some space, and I'm going to say x3 equals to y1. I should have put 1 there. Sorry, y2 here. And then we're going to say x4 is equals to y2 dot. Okay, and one thing we can add, and then we're just going to add it using green, is that y1 dot is just x1 dot, and y2 dot is just x3 dot. This might turn out to be useful right at the end of when we're solving our problem. So again, we have 4 state variables. That's something worth noting. And that was something easy to identify just by looking at our system and seeing which variables are, with respect to time, being differentiated. Okay, so now we move on to actually solving the question and coming up with differential equations. And so we're going to take it one step at a time. So this is how we do it. We say for mass 1, the sum, and I think I should use a red pen here. This should be more easier to distinguish. The sum of the y forces And we can look here for the mass 1. So remember, we have that spring K1, damper C1, and we have the external force P and the mass, yes, and the mass itself. Okay, and then we also have the spring acting downwards. Okay, so this means that the sum forces is equals to M1 Y1 plus P of T, and this is just going to be a lot of algebra, so feel free to skip forward if you want to see the end of the you want to see the final equations and the matrix equations. So these ones are going to be K1. I hope you've drawn, because I won't be scrolling up much. I have it written somewhere on paper. I have this diagram drawn somewhere on paper for quicker working out. C1Y1 dot, that's M1 P of T, which is K2. Hopefully I'm writing this correctly. Okay, let's see. So we have K1 Y1 plus C1 Y1 dot, okay, that seems about right, is equals to M1 Y1, which is that, and that's the middle spring. Since Y2 is greater than Y1, it looks like that, and that's what we were discussing here. So this interaction force here just simplifies to this. Yeah, it simplifies to this. Let me just encapsulate it with this. Okay, so that's the first one, and we can now expand it in terms of our state variables. And do we have to feature our input? Yes, we have to feature our input. I forgot to specify that we're gonna let this one equals to, we're gonna name this as U, because that's our input. So this becomes, using red again, or yeah, I think it should be enough to use red. Might have to, yeah, okay, I think I'm gonna skip some parts here, but for this one, just for everyone to understand, it's going to be K1 X1 plus C1 X2 is equals to M1 X2 dot plus U plus K2 X3 minus X1. Okay, so now I'm going to use a blue pen, which means we're going straight to the final answer. So what you have to do now is you have to rearrange this to make X2 dot the subject. So we're going to have an answer like this: X2 dot the subject is equals to minus K1 plus K2 all over M1, I think, yes, and X1 minus, let me see, C1 over M1. You'll forgive me for skipping some steps, but I think I just skipped one step. But this is to keep the video short, because this is, like I said, it's a big example, and it's a big problem. And I just want to keep it no less. I would like to complete this video in no less than 30 minutes. Okay, X3 plus 1 over M1 over U. Okay, and this is for mass 1. As we'll just underline that. Now we move on to the next one. Okay, so for mass 2, same stuff. Let's go back and look at it. For mass 2, we're going to be looking at the sum of the forces acting here in the y direction. So I will write this in red again. Fy plus the middle spring. So now you'll notice that the middle spring is being added on the left hand side, because now for this force, it's acting upwards. It's not acting for the first one. It was on the right hand side because it was acting downwards on the first mass, but on the second mass it's acting upwards, so it's gonna fall part of that. Okay, so we just have one thing acting downwards, which is just the weight of the mass. Okay, so now we have that, and we only have, actually, looking at this second problem, only the spring is working upwards. So on that right hand side, so the forces here is actually 0 plus the middle spring on its own. It's doing all the carrying. Okay, K2 Y2 minus Y1 is equals to M2 Y2, and that should do it. And then now all we have to do is replace all the y's with the state variables, and that simplifies to something like this. And I haven't skipped a step. I'm about to, but I haven't skipped yet. K2y1 is equals to M2, and that's going to be x4 dot. Okay, and then I will skip a step and go to the final. So here, just like the previous part, we're going to make our first derivative here into the subject. So we got x4 dot is equals to minus K2 over M2 x1 plus K2 over M2 x3. Okay, and now we are done with that. So next step, I'm just gonna write this in black. And say next step, we would like to have our we would like to have our x dot ax plus bu, and our y is equals to cx plus du, matrix equations. So this should be easy. What it requires now is for us to just copy our two blue equations here into the matrix, into matrix forms. This shouldn't take too long. Okay, so I think I'm gonna write it in blue. Yeah, because I think I'm liking blue now. Let's see. So we have x1 dot, x2 dot, and I think there should be enough space. x2 dot, x3 dot, x4 dot. Okay, move this a bit down. Okay, so you'll notice that we actually found x4 dot and x2 dot. So where is x3 and x1 dot? We did express them here. That's why I said this will be helpful a bit. Okay, so now we just have to copy everything across. So let's start off with, I think we'll start with x2 just to see how much space we're going to need. And that's going to be k1 plus k2 all over m minus c1 over m1, and that's going to be k2 over m1. If it doesn't fit here, I'm gonna make a plan. It has to fit, and that's gonna be 0. Yeah, I think I should just slice this, shift it to the right, shift it to the left. Yeah, should sit nicely. Okay, and I'm gonna look at x4 minus k over 2, k2, sorry, and m2. And we're gonna have 0 there, and then we're gonna have k2 over m2. We're saying m2, yes, it is m2. We're gonna be 0, so this is gonna be 0, 0, 0, 1, and this is gonna be 0, 1, 0, 0, and that looks very ugly. Apologies for that. And yeah, x1, x2, x3, x4, still with a bit of space, plus, and this is going to be the last part, 0, 1 over m1, 0, okay, and that is our first equation. This is the state equation. So now for the output equation. So for the first time in our examples, we have a proper output matrix or output vector. It's a column vector, more than one output. Very exciting stuff. And 1, 0, 0, 0, and that's going to be 0, 0, 1, 0. I hope this is going to be easy to understand where we got it from. And this is going to be x1, x2, x3, x4. Let me see if this matrix works. So multiply across, multiply down. Let's see, 1 multiplied by that, that's going to be okay. So y1, we did say it's equals to, where is that? I wonder if we did stay. Yes, y1 is equals to x1, sorry. y1 is equals to x1, so it is, yes, and then y2 is equals to x3, yes. So this is perfect. So this is our state space model for our overly complicated, not too complicated honestly, mechanical system. So it is not exactly challenging. What was challenging, I guess, it was just doing all the algebra work and trying to fit everything into these two equations. So hopefully you have been able to do it, and then you'll try to challenge yourselves and do more difficult example equations that you should find easily in textbooks and on the internet. In the next video, we're going to be moving on. We're going to start talking about finding state equations from transfer functions. So that will be converting from the frequency domain to the time domain, particularly in the state space. Until then, take care.